We want to go live now?
Sure. Okay, hello everyone. Thank you all for coming to the MATH1081 revision seminars. My name is Fred. Today we've also got Ronald and Bruce. The revision seminar is going to be two parts. So part 1 is going to cover the first 3 topics, and part 2, which is going to be on Thursday 2 to 4, will cover the last 2 topics. And for the style of these seminars, we're mainly going to be focused on covering and past questions, showing you guys the ways of approaching and answering the different exam questions. So the first topic here we have sets and functions. And for part A, suppose A and B are sets with the size of A equals 2 and the size of B equals 3, and we want to find these sizes over here. So the first property that you'll need is the size of power set, and that's going to be given by 2 to the power size of A. And the second property that you need is the size of a Cartesian product. And how I remember this is that so the size of a product is the product of the size. So part A, we're first looking at this first expression over here, and you can realize that you're going to need that size of a Cartesian product formula. And using that, we can split it up into 2 different parts. And now you can notice that we have the size of the power set, and here you can use the size of power set formula. So that's going to be 2 to the power A times 2 to the power B. And we know what the sizes of A and B are, so here we can just plug the numbers in and we should get 32 as our answer. And so pretty simple for the first one. Let's have a look at the second part over here, and this time we're looking at the power set of A times B. So it's the same process, we're using the same formulas, but it's mainly just different ordering. So here we're first using the size of the power set formula, and that's going to give 2 to the power A times B. And notice we can now split that out. That gives 2 to the power A times 2 to the power B. And here, this is just the process of plugging in our numbers, and we should get so a pretty simple case for part A here. So for part B, that this inequality holds for all non-empty finite sets X and Y. So the question didn't ask us to prove whether this is true or false. It's asked us to determine if it's true or false. So with these questions, there are mainly 2 parts. Part 1 is going to be like an investigation to determine whether it's true or false. And part 2, it's going to be like our formal proof to proving it's true or false. So part 1 is going to be our investigation. And the investigation mainly involves just playing around with our inequality to see if we can deduce a contradiction, or maybe deduce an identity that is true. So here we have P of X times P of Y. It's less than or equal to P X times Y. So here again, for the left-hand side, we can split it out using the size of the product formula. And on the right-hand side, we can use the size of the power set formula. So, Y. So, back on the left-hand side, we have the size of power set. And again, we can simplify that down to 2 to the power X times 2 to the power Y. It's less than or equal to 2 to the power. On the right-hand side, we can split out the Cartesian product. So times Y. So back on the left-hand side, we have 2 product that we can combine using our indices laws. So we have 2 to the power X plus Y. It's going to be less than or equal to 2 to the power X times Y. I'm out of space. Oh wait, can I make the page? You don't know? Okay, so I'm going to, this will be a problem. Maybe you create a new page. Just Raise it? I don't want to raise it.
No, that's the function. Do you want to control that? So, yo.
It's the chalkboard. It's the chalkboard, the blackboard.
Chalk. Oh, no, because the online people can't see then. Because we're streaming online as well.
Yeah.
You don't know how to fucking do it. Alright, whatever. So, okay. So we can't create a new page, so we're just gonna erase everything out. Wait, can we make it bigger? Make the eraser bigger. How do you make the eraser bigger?
Yeah.
Alright, so
Just painstakingly do it, it's fine.
okay, so we had 2 to the power x plus y is less than or equal to 2 to the power x times y. So since we know that the exponential function is increasing, we can just equate the powers here. And so we get to this over here. And so you just look at this, and you say, is it true for all non-empty finite sets x and y? And you think about it, and what happens if x equals y equals 1, if they're both 1? So then our left-hand side equals 1 plus 1, which is 2, and our right-hand side is 1 times 1, which is 1. So clearly, our left-hand side is bigger than right-hand side, and so we have essentially found a counterexample to proving that it's false. So we can say that statement is false. False by counterexample. So here we can just give an example. So we have size of x equals size of y equals 1, and we have left-hand side equals power set of x times power set of y. And again, we're just using our same formulas from our part 1 investigation, just now with our known x and y's. So we have split this out, and we should get this over here. And again, we have the power set, the size of the power set.
You can copy and paste power slides with CV and
Siri.
Control
C.
Yeah, it should be yo. And then so and one of these. And then yeah. So I made a copy of that.
Wait, how does it work?
So you go here. And then you CV.
Oh shit.
And then it comes up.
shit. And then we just gotta rub it out there.
Yeah.
Alright, sweet. Okay. So again, back to our question, we have again size of power set that we can use our formula. That's going to be 2 to the power x times 2 to the power y. And so now plugging our numbers in, we know that size of x equals 1 and size of y is also equal to 1, and that is equal to 4. So, and now we want to evaluate our right hand side. Wait just a second.
Sorry, just give me one moment. I'm going to change the settings here. Okay, cool. That should be better.
Sweet. Okay, so now we want to evaluate our right-hand side. So we have, so let me go back. Okay, sweet. So now our right-hand side is going to be right-hand side equals size of p times x times y, And here, it's going to be the same formulas again. We want to use our size of the power set formula. And here, again, we can split these out. And now we can plug our ones in. And that's going to be 2 to the power 1 times 1. And so that's going to equal to 2. So we have our left-hand side.
You can't write while he does. Wait, sorry.
Yeah, sorry guys, just
Yeah,
bear
thanks
in
for
mind
very-
we have a few technical difficulties. Give me just one moment to sort it out.
Yeah, because like, do you see this? This looks like this. So it's copying nicely. I think you just make it smaller and then you move it to the side. So like, we know.
It was the window capture. Just go back to it.
I'll continue.
Yeah.
Sweet. So again, our left-hand side was equal to 4, and our right-hand side equals to 2. So clearly, our left-hand side is bigger than our right-hand side, and so essentially we have found a counterexample that disproves the statement. So it's not true that inequality holds for set non-empty finite sets x and y. And here we got the formal solution. So again, part 1 is going to be your investigation, and part 2 is going to be your formal proof, disproving the statement. Okay, so next question we have is use the laws of set algebra to simplify this expression over here.
We'll just take 3. Yeah.
That's fine.
Yeah, I'm 90% sure it should be fine.
Alright, sweet.
Yeah. You can see this. Oh no, it's
Cutting
cutting.
in.
It's cutting out here.
So I have to zoom out.
Yeah.
Oh,
I think
right.
No, it's just a delay.
Alright, sweet. Let's just continue. So here, first thing you want to notice is that we have a intersection B. Oops. We have. What the hell? It's not sinking in. Wait, is it meant to be bigger?
You can't. Yeah.
Wait, this was changing size as well. So, like,
I think you.
that's not changing.
This
down.
isn't.
I don't know what's going on.
Yeah. It should be mirroring. And then you can't write anymore here. So I think this screen's frozen.
Why is it frozen?
Yeah. Quite the L.
Oh my god, dude. Fuck me dead.
Nah, I'm good.
Try it again.
What are you trying to do?
The screen
froze now.
Oh, okay.
And
Oh, sweet, that's back. Alright, we're back. So, back to the question. First thing you want to notice is that we have A intersection B complement the whole thing, and
yeah,
we
you
can
can see the whole thing now.
oh,
Yeah.
zoom in.
You can see the whole thing now, yeah.
Zoom in. Sweet. So using, if you know the Morgan's law, so that's going to be equal to, that's equivalent to saying A intersection. So using the Morgan's law, we flip both, I guess we negate both the A's and B's, and we flip the intersection sign to a union. And that's going to be union with the complement of B. So here, notice that we have, I guess, intersection on the outside and union on the inside. And here we can use our distributive law. And so here I'm going to quote De Morgan's. And so if we use our distributive law, we can expand this out. So we get not B union with complement of B, and it's going to be distributive. Right, so again, here we have A intersection with the negation of A, and notice that's going to be the empty set. So we have empty set union with A. I should use BC, union with BC, and this is going to be your intersection with complement. Okay, so empty set union with anything, that's just going to be the same thing. This is known as your identity law. So identity. And so let's create a new page. Okay, sweet. Okay, so notice that we have so A intersection B union with complement of B. So here we notice that we have an intersection on the outside, on the inside, and a union on the outside, and we have the complement of B both on the inside and outside. So if you know this is actually just the complement of B from your absorption law, and this is probably the hardest to see, but it might be easier with a diagram. So if you have, say you have X union Y, and let's draw a Venn diagram. We have X, Y, and that's going to be this whole region over here. And if we again intersect this with X, and so that's just going to be this. No, that's going to be this original set over here. Right, and same for the other way. We have, if we have X intersection Y, that's going to be this bigger. That's going to be this center section over here. And then if we again union this with X, that's going to result in the original X set here. So this is your absorption law. It's probably the hardest to see, but if you're good, you would see it really easily. So sweet. And this is your formal solutions, and it, as you can see, simplifies down to the complement of B. Okay, so next question is if X and Y are sets with size of X equals 2 and size of Y is n, how many injective functions are there from X to Y? And this actually ties in with topic 4, your combinatorics. So it's a really nice question that uses a mix of different topics. So injective function, how I like to think about it is that if the outputs are equal, then the inputs are also equal. And for the surjective function, in simple terms, it's just every element in the codomain is the function value, or in other words, the range equals the codomain.
Yeah, just making it bigger.
Yeah, sweet. Okay, so part A, we want to find how many injective functions are there from X to Y. So if we have this function that goes from X to Y, and we're given that the size of X is 2, so we have two elements, and we call it A1 and A2, and so size of Y we're given is n, so we have n elements. We have B1, B2, all the way down to Bn. Now firstly, since f is a function, there must be an outgoing arrow out of each element in X, and we're asked how many injective functions are there. Right, so like what we don't want, right? What we don't want is if every value in X if both A1 and A2 point to the same element in Y, that's like something that we don't want. So here it's sort of a game. We want to first find two elements in Y that I can map towards. So if you notice, that's going to be in choose 2. Out of the n elements, I want to choose 2 for A1 and A2 to map towards. And notice that ordering actually does matter. So if we have A1, A2, and B1, B2, this is actually going to be different to if A1 maps to B2 and A2 maps towards B1. So in this case, ordering does actually matter. And so we have to actually times by 2 factorial. And if you simplify this down, this would actually turn into n times n minus 1. And yeah, that's going to be the number of ways, number of injective functions from x to y. So for part B, this time we're asked how many surjective functions are there from x to y, and we flip the sizes around. So we have function f from x to y, and this time in x we have n elements. So we call this a1, a2, all the way to an, and in y we have 2 elements. We have b1 and b2. Again, since f is a function, there must be an outgoing arrow in every element of f. And we asked how many surjective functions are there from x to y. Again, if we consider the cases what we don't want, there are actually 2 cases that we actually don't want. A1, A2, down to an. And the 2 cases are if every element in x map towards the same element. So if all the elements in x map towards b1, or if they all map towards b2, that's going to make it not surjective. So we have 2 cases where f is not surjective. So here it would be really nice to use the complement. So we first need to find like the total number of functions that we have, and if we consider each individual element in x, notice that a1 has 2 elements that you can map towards, and same with a2 and all the way down to an. And so this is going to be 2 times 2 times 2, where we have n terms over here. Right, so number of surjective functions, that's going to be the total functions, which is 2 to the n, minus the 2 cases where f is not surjective, and that's going to give us 2 to the power n minus 2. Sweet. We're moving on to inverse functions, and here's a theorem that a function g from y to x is an inverse of f x to y, if and only if both g of f and f of g are the identity map. So here what we want is g of f, and if we evaluate this at x, that's going to give just x. It's for all x in the domain. And again, we want f of g, and if we evaluate this at y, that's going to return y, and for all y in y. So the question here, 2017, let f be a function, and let f and g be both functions defined by fx is ln x plus 1, and for that domain, and g of y is e to the power y minus 1 for y in the reals, and we want to write down the domain and codomain of g of f. So g of f, if we evaluate this at x, that's going to be g of f of x. And notice that the domain of g of f, that's going to be the domain of f. And similarly, the codomain of g of f, that's going to be the codomain of g. So we have, again, g of f is going to be defined since the codomain of f is a subset of the domain of g. So we have these domain and codomains, and part B is we want to prove that g of f is the identity map on 1 to infinity. And here we can just use g of f, evaluate this at x, and show that it's equals to x, right? So again, g of f of x, that's going to be g of ln x plus 1. And here we just need to sub in ln x plus 1 into g, and we get e to the ln x plus 1 minus 1. Simplify that down, it's going to be e to the ln x. And since we know x is positive, that's going to simplify down to x. So we know that g of f evaluated at x, that's going to return x. And so we can say g of f is the identity map on 1 to infinity. Now, part C, is it true that f is the inverse of g? And here is where you want to use the theorem that both g of f is the both g of f and f of g is the identity map. And in part B, we proved that g of f is the identity map for x from 1 to infinity, but we also have to prove that f of g is the identity map. So notice that we have f of g, and then evaluate at x. It's going to be f of g of x. So for this to be defined, we need that the range of g to be a subset of the domain of f. So if we look at the range of g, so we have the range of exponential, and that's going to be the positive reals. So it's going to be 0 to infinity, and we know that the domain of f, that's given to be 1 to infinity. So clearly, the range of g is not a subset of the domain of f, and that tells you that f of g doesn't even exist. And so f cannot be the inverse of g. So f of g is not defined, and yeah, it can't be the inverse. And sweet. So next question here we have from 2018, and let f from r squared to r be a function defined by f of x and y equals x squared plus y squared. And for part A, suppose that s is a unit square given by this Cartesian product over here, and we want to find f of s. Here, for part A, it's good to definitely consider this in terms of a Cartesian plane. So we have a plane x, y, 0, and we're taking the Cartesian product of all the numbers between 0 and 1 inclusive. So we have 0, 1. And if we take the Cartesian product of these two sets, that's going to give the area of this whole unit square. This corner is going to be 1, 1. And here we want to find f of s. So if you imagine we input like a region into f, that's also going to output like a range of values. So it's best to find the min and max values of f of s. Sorry. So min of f of s. Now notice that f is defined to be x squared plus y squared, and that's sort of like bringing back like I guess size of a vector or like size of a complex number, and we want to find the min of this. So if we just take the point of the origin, so 0, 0. That's going to be f of 0 0 squared plus 0 squared, and that's going to equal to 0. So at the point of the origin, that's going to give you the mean value of f of s. And similarly, we can find the max value of f of s. And we want to find the point in the unit square such that f of s is a max. And if we go out all the way to the top right corner, notice that the vector here, it's going to give the max length. So the point 1, 1, that's going to give the max value of f of s. And if we evaluate this, that's going to be 1 squared plus 1 squared, which equals to 2. And so, if we imagine that we have a min at 0 and the max value is 2, then we also have every single value in between that can also be mapped towards. So we can just say,
Yo.
Can you do arithmetic on ranges? So like you want 0 to 1 squared plus 0 to 1 squared.
Oh.
And then you do like 0 plus 1, 0 to 1 plus 0 to 1 is 0 to 2.
yeah, that also works.
Repeat the question. Repeat the question. It's on the stream.
Also, he wants to like, I guess, okay, so we have 0 to 1, I guess, and 0 to 1 to 1, and then that's going to give us, if you consider 0, 1, we have 0, 1. So here, the top one, that's going to give out every, I guess, the x-axis here, and the second one, that's going to give out this section over here. So again, and if we sort of swap the order around, so set. This one is going to give out all these values, and if we have 1, it should be a set. That's going to give out the right hand side. So every element in between is also going to be mapped, and that's like the same idea. Okay, so we have the min of f of s as 0 and the max equal to 1. So, and since we know that every element between can also be mapped towards, f of s, that's going to be a set of numbers between 0 and 1 inclusive. 0 and 2, sorry. Right. And so for part B, we want to find and sketch f inverse of a set of numbers between 1 and 2 inclusive. So here, again, you want to use that min and max idea again. So if we consider f inverse of 1, so we want to find values x and y such that x squared plus y squared equals 1. And similarly for f inverse of 2, we want to find values x and y such that x squared plus y squared equals 2. So notice that x squared plus y squared plus equals 1, or it being equal to 2, that's going to be a circle set at the origin, radius 1 and root 2 respectively. So if we sketch out this graph, let's draw our Cartesian plane, and we have our first circle being the unit circle, and our second one being a little bigger. And first one has radius 1, and the second one has radius root 2. And since we can input every number between 1 and 2, so we have f inverse 1 and 2. So every number in between 1 and 2 can be included. So imagine this is going to be, we're going to start at this unit circle, and we're going to slowly increase our way out to the outer circle. So that's going to map out every, every circle that has a radius 1 and 2, or in between. And that's going to generate sort of like an annulus shape. This is going to be like a sketch. And if we want to, give like a formal definition, we can say this equals to set of all points on the Cartesian plane such that 1 is less than or equal to x squared plus y squared, and that's less than or equal to 2. Right, so we want the area to be between the two circles. And here we've got the solutions, and same idea, it's going to give out the annulus shape. Okay, next question here we got is from 2020, and a function is bijective if and only if it is both injective and surjective. So again, if we want to prove a function is bijective, we would prove it's both injective and surjective. So the question here is let B from the reals to reals be defined by Bx equals this degree 13 polynomial, and the question is show that B is bijective. So firstly, again, we want to prove it's both injective and surjective. So for injectivity, normally you would prove that f of x, in this case is b, so b of x1 equals b of x2, and this implies x1 equals x2. But in this case, we have to deal with the degree 13 polynomial, and it's not really ideal to use this. It's not going to get anywhere. And you have to think of another method to deal with this. Right, the first thing I want you guys to notice is that we, for the powers of x, we have x to the 13, x to the 3, and x to the 1. And notice that they are all odd numbers. So if we consider the derivative of b, that's going to give out 13 times 14, I'm not sure what that is, but x to the power 12 plus 33 x squared plus 19. Alright, so we have x to the 12, x squared, and then plus 19. And notice this is going to be bigger than 0, right? So x squared, x to the even power, is going to be bigger than or equal to 0. But since we have a plus 19, that's going to force it bigger than 0. And so since we know, since b dash x is bigger than 0 for x in the reals, we know that b is increasing on R. And that's sufficient to say b is injective. Alright, so second part is we also have to prove surjectivity. So this one's slightly more tricky. And sort of idea that you want to go for is you want to think about the range of b. And notice that we have b being a degree 13 polynomial, or in other words, b isn't the degree of b is odd. And we know that it's increasing, so it's going to look something like starts with negative infinity and goes towards positive infinity. We know that the range of b is going to be all the reals. Range of b, that's going to be all the reals, and the codomain that's given to us. And since we know that the range equals a codomain, then it's going to be surjective. Right, but we have to write a more formal proof of this because we're dealing with infinities. So here we have to say that we know that limit as x approaches infinity of b of x, that's going to be infinity, and same with negative infinity. So write this here, limit as x approaches negative infinity. That's going to be negative infinity. Here we actually need to go back to our formal definition of the limit, and here we're actually dealing with infinities. So we know these two statements are true, so the formal definition, so for y being in the reals, there exists an m bigger than 0, such that if x is bigger than m, then b of x is bigger than y. And the first one here, that is dealing with the positive infinity case. Notice we also have a negative infinity, and how we can write this is if x is less than minus m, then we can say that b of x is less than y. So we have every function value mapped out. And here, one thing that we can apply is the intermediate value theorem. So by the intermediate value theorem, there exists x in between minus m and m, such that b of x 0 equals y, and that is for all y in the reals. And since this is true, we can finally conclude that the range of B is the all reals. And this is going to equal to the codomain of B. And so, since we have the range equals the codomain, we can say thus B is surjective. And since we know that it's both injective and surjective, we can say that we can finally conclude that it's bijective. And that is it for this question. And this is the formal solutions. Again, we can prove it's increasing. And for the surjective, we can prove that the range equals the codomain. Okay, and that is it for topic 1. The next topic that we're going to go through is integers, modular arithmetic, and relations. And for now, I'll be passing it over to Ronald, who will be presenting this topic.
You're lucky. Right, thank you guys all for coming, and thank you so much to Fred for presenting for us, and also for you guys bearing from technical difficulties. And I might go over time, so I'll just try to make this as fast as possible. And feel free to ask any questions. Like once the question's ended, you'll see like a slide that looks like this, which is going to just state the next question. And yeah, that should be. Yeah. Okay. So the first question is just a simple one. You'll see this in your exams, like basically all the time. And this is something you should have seen in your lab test as well. It's to evaluate 2015 to the power of 1082 mod 11. So the main way you can just do this is just seeing a pattern within the powers. So, you just look at the first power of 2015, and we see that it has the equivalence of the equivalence of 2 in mod 11, and you can just check this by using a calculator. So on the calculator, I just typed in 2015 divided by 11, and then you press the equal sign, and then you press minus 183 equals, and then times 11, and then that gives you the remainder. So you can also try this in your own time. These slides will be uploaded to our website and stuff, so just check it out afterwards. So we can just do this with more powers. Let's try the second power. So we see that if you square both, you can use this property where if A is equivalent to B mod M, then a to the power of n is also equivalent to b to the power of n for mod m, which is how we found 4. So we can do this for more powers of 2015. And this is just a table. You essentially just keep going until you find the power which has the equivalence of 1, which you can see right here, which is the 10th power. So you just say that there's a cycle of 10. The reason is, if you go to the 11th power, it's actually going back to 2, and then it starts this cycle all over again, and then it goes back to 1 at 2015 to the power of 20. So we can just take the mod 10 value of 1082, which is equal to 2, and then we know that this is equal to 2, and it's equal to 4 right here on our table. This is another question that you might find in your exams, which is finding the GCD of two values, the greatest common divisor. So here it's 105 and 342. So we use something called the Euclidean Algorithm, which essentially just breaks up a number into its quotient and remainder. And, so we can divide 342 by 105 and get 3 and then a remainder of 25. We can then put it into this form right here. And then we take the number 105 here and the remainder, 27, and just apply the Euclidean algorithm again. And we essentially just keep going until we have no more remainder. And this number right here becomes our greatest common divisor, since we have this property that the greatest common divisor of A, B, and the greatest common divisor of BR are equal. So you can just keep going. So you look at the first two numbers, which is 105 and 342 we had, and then we had 27 and 105, and then we had 24 and 27, and then we had 3 and 24, all of which had a greatest common divisor of 3. So now we can solve or explain why there's no solution to these equations. They're called equivalence equations. We use something called Basos Identity, which requires a equation to be transformed into this right here, ax plus by equals c. So this is a form where a, b, and c are integers, and a and b are both non-zero. So the number of integer solutions to this type of equation can be found by taking the greatest common divisor of a and b, and if it doesn't divide c, we know that there are no solutions. And if it does divide c, there are a GCD a-b amount of solutions. So when we want to check solubility of a equation, we refer to Basos Identity. And these two forms are essentially equivalent, where in this case y is just some integer. So let's look at the first equivalence equation we have, which is 105x is equivalent to 9 in mod 342. We can transform it into this equation that we had from the last slide, and then we divide everything by the greatest common divisor, which is 3, and we use Basos Identity. So we see that the greatest common divisor is 3, which was in part A, and since it divides 9, we know that there are 3 integer solutions. So we do what I said before, which is you take this equation right here, and then you divide all terms by 3, which should get you an equation that looks something like this. So we can apply the Euclidean algorithm, which gives us these 4 equations. And then we use something called the extended Euclidean algorithm, which basically states for the two numbers right here, there should be a way to express the greatest common divisor with these two numbers times integer multiples. You'll see what I mean in the next slide. So we have 1 is equal to 9 minus 8, and then 9 is equal to 35 minus 3 times 9, and then you keep subbing these solutions, and then you can collect the terms, right? And if you see, the 9 minus 8 here actually comes from this equation right here, and we also use this equation to make 8 the subject and 9 the subject. And then we just sub it in, so we subbed in this 9, and then we subbed in the value of 8 here, this value of 9 here, and then we just collected the terms. And then we have this equation where 1 is equal to 35 times minus 13 plus 114 times 4. So from our previous equation, we needed a 3 on this side, right? And then just 35 times the number, then plus 114 times the number. We can get 3 here just by multiplying both sides by 3. And then we can collect the 3 into the actual term here. So we multiply the minus 13 by 3, which we get minus 39. And then we multiply the 4 here by 3, and then we get 12. Now we have this equation, which we got from the original. And then what we can do is we can equate coefficients. And so we find that x is equal to minus 39 is an integer solution. But for these equations, the solutions have to be from 0 to 342, where 342 is the original mod right here. And a little trick we can do is to add the number over here, which is 114, to the x repetitively, whilst it's still below this 342 number. So we add 114 to this number, but we can also add it again and again, since we know that there are 3 solutions, right? So you just keep adding it until, if you add it once more, this will actually go out of our range right here. So these are the 3 solutions. So now we can look at this equation right here. 105x is equivalent to 8. And so we can transform it into this equation, which we had from the previous slide. We know that the greatest common divisor is 3, but 3 doesn't divide 8. And simply, we just say, hence by Basos Identity, there's no solutions for this equation. Also, like, tell me if I'm going too fast or anything, and you want me to slow down, go back to something else, you know? So, for this question, it states, suppose that the greatest common divisor of a and b is d. Show that if x is a solution of ax, which is equivalent to b mod m, then so is x plus m on d. So, a good way to use these proof equations is to just suppose what the if statement is. So we can suppose that ax is equivalent to b mod m, and then we can also look at what we need to prove, which is that this is a solution, right? So it would also mean that you can sub it into this equation right here, which is what I did. So we subbed it here, and then we said that it's equivalent to b. Now, what we can do is we can look at the left-hand side of this equation, which gets us this, which is expanded out to see that a times the number up here is equal to ax plus ma on d. So we know that the greatest common divisor of a and m is d, so a on d must also be an integer. So we can then say that these two are equivalent, and since a on d is an integer and there's an m right here, it actually just gets absorbed into this mod m right here. So we can say that ax plus m times an integer is equal to ax in the world of mod m. And then we know that ax is already equivalent to b in the world of mod m, so we can just say that it satisfies this equation where a times that number is equal to b and is therefore a solution of this equation up there. So this question wants us to say, given that, so the symbol up here, to the power of minus 1, it just means inverse, and I'll explain what an inverse is later, but the inverse of 1039 is 31 mod 2013, so we need to find integers k and l such that 1031k plus 2013l is equal to 1. So an inverse is just a number such that a times its inverse is equivalent to 1, in mod M. So that gives us the equation 1039 times 31 is equivalent to 1, 2013. And then we can just turn it into this equation, which we learned previously. Now, we can see that this looks really similar to the equation up here, except we know the k value right here, but we don't know the L value since it's just an unknown y, but we have one equation and one unknown, so we can just solve for y, and that gives us minus 16. So we have this equation where we equated 1 to this, and we found out that 1 is also equal to this. So we can compare the coefficients, so we know that k is equal to 31 and L is equal to minus 16 are valid solutions. So we need to find the general solution of 1039x plus 2013y is equal to 4. And we can do this by just multiplying both sides by 4, because it would get the right-hand side to become a 4 instead. And then we multiply each of these terms by 4, which gets us 124 and minus 64. Then we just equate it to the equation up here, and then we can just equate coefficients. So a possible solution is x is equal to 124 and y is equal to minus 64. So we learned previously that a trick we can use is just adding an integer number of 2013s, which is the number right here. And this is our general solution for x. So the way we find the general solution for y is just considering the fact that when we expand it out, it's equal to 1039 times 124 plus 1039 times 2013z. And then we can just see that if we put this term to the other side, we're just left out with this term, and then that term plus 2013 times 64 is equal to 4 from our last equation. So we can actually just take this term, and then we put it into this 2013 right here, which gets us minus 64 minus 1039z. So then we can just equate it to our original equation, and then from equating coefficients, we have a general solution of x is equal to 124 plus 2013z, and y is equal to 64 minus 1039z for some integer z. So we have this relation that's defined on the set real times real, which just means that it's an ordered pair where both numbers are real numbers. And A1, B1 is related to B1, A1, A2 is related to B1, B2 if and only if the the sum of the squares of both numbers is equal to the sum of the squares of both numbers. How can we prove this is an equivalence relation? We have a couple properties and types of relations that we can draw from. So let R be a relation defined on set A. The reflexive property just means that every single element in the relation relates to itself. The symmetrical property says if one element relates to another, the other element must also relate back to the original element. So, if it works one way, it should work vice versa. And the anti-symmetrical basically says if it works one way and it also works vice versa, x and y must be the same element. So the transitive property just says if there's one element and it relates to another, and that another element relates to a third one, the first element must relate to the third element. Now, there are two types of relations, the first one being an equivalence relation, which means that it's reflexive, symmetrical, and transitive. And then there's the partial order, which is reflexive, anti-symmetrical, and transitive. So to prove that it's an equivalence relation, we need to first prove it's reflexive, which is all terms relate to itself. So we can just let A1, B1 be real numbers. And then we know the fact that a1 squared plus a2 squared is equal to a1 squared plus a2 squared. And by this definition, we can say that a1, a2 is related to a1, a2. Since a1, a2 is just any single ordered pair from real times real, we can say that this is a reflexive relation. So then we prove its symmetry. So we define two ordered pairs, a1, a2, and b1, b2 as real numbers. And we can use this definition of symmetry where we suppose the if statement, where a1, a2 is related to b1, b2. So by definition, we can say that a1 squared plus a2 squared is b1 squared plus b2 squared. And we also know that that means that b1 squared plus b2 squared is equal to a1 squared plus a2 squared. That means that b1 and b2 is also equivalent to a1 and a2. And since a1 and a2 and b1 and b2 are just like any ordered pair in real times real, we can say that this relation is in fact symmetrical. So now we need to prove the transitive property, where if one element is related to another and the other is related to the third, the first is related to the third. So we define three different ordered pairs. So we define a1, a2, b1, b2, c1, c2, and they're all real numbers. We assume the if statement. So a1 and a2 relate to b1 and b2, and b1 and b2 relate to c1 and c2. And then we get these equations. And then we can just say that a1 and a2 is related to b1 and b2 because the square of these two numbers is equal to b1 and b2 all both squared, and it's also equivalent to c1 and c2 both squared. And since the first element's related to the third, we can say that it's transitive. So we know that the relation is reflexive, symmetrical, and transitive, which allows us to say that tilde is indeed an equivalence relation. So we need to give a geometric description of the equivalence class with 1O. And an equivalence class is defined by the equivalence class of A being the set of all x within the original set A such that x relates to A, where A is just some element in A. Well, small a is some element in big A. So we have the equivalence class of 1, 0, and we know that it must be some ordered pair in the real times real, where the ordered pair is related to 1, 0. So we have the definition here where a1 squared plus a2 squared is equal to 1. For some real numbers, this should be a2, sorry. And we can just see if we sub in these new values where a1 is equal to x and a2 is equal to y, this actually just gives us the equation for a unit circle. So we can just say that the equivalence class with 1 and 0 as the ordered pair is just a set of all ordered pairs which contain all the coordinates on the actual unit circle. So, is it true that all equivalence classes are infinite in size? Explain. So, there are two cases, right? Either all of them are infinite and you have to prove that, or all of them aren't and there's like some random case where it isn't. And in this case, of course, usually it's going to be the fact that there isn't. So we just need to find that case, and we can consider the equivalence class of 0, 0. So by definition, the square of both numbers is equal to 0 for some real number a and b, is a1 and a2. And that would mean that a1 squared is equal to a minus a2 squared, where they're both greater than or equal to 0 since they're both squares, right? Now, this gives us the fact that a1 squared is greater than, we can suppose that a1 squared is greater than 0, which would mean that minus a2 squared is also greater than 0. This would give us the property that a2 squared is less than 0, and this contradicts our original statement since it's the square of a real number, so it has to be greater than or equal to 0. We can also argue this for a2 squared is greater than 0, and this basically just proves that if a1 squared or a2 squared are greater than 0, then it just doesn't work out, so it can't be greater than 0, and the only other case is being 0. So a1 squared and a2 squared must be 0. And since there's only one element in this equivalence class, it contradicts our statement since, it has a size of 1. And obviously, if it has a size of 1, then it's not infinite. Yeah?
So you can't go straight from a squared plus b squared equals 0 to a equals b equals 0. So you have to actually prove all considering cases.
If you want it to be more rigorous, yeah. So the question was, can you just assume that a1 squared plus a2 squared is equal to 0 is the case where a1 and a2 are both 0? Well, you can probably do that by just graphing it. So we know that it has to have a radius of 0, so the only way is for the point to be only 0, 0. And that's another way. But, since we don't have any graphs, we just want to be rigorous, just make sure that they don't take away any marks from us, So, we have the relation star, which is defined on the set of integers, z, where if a star b, if and only if a squared is equivalent to b squared mod 4. So, given that it's an equivalence relation, find all of its equivalence classes. So, we know what equivalence classes are from the last question, and to find all of the equivalence classes, we need to find it such that the union of all equivalence classes is equal to the original set, which is z. And we'll get what that means later. So we're in the world of mod 4, which means that all of the integers can be represented as 0, 1, 2, and 3. So these are all the cases that we need to check. So if x is equivalent to 0 mod 4, that means x squared is equal to 0 as well in mod 4. And that means all of the integers such that a is equivalent to 0 mod 4 are in the equivalence class of 0. So these are all of the numbers in the form 4n. So that's -8, -4, 0, 4, just all of the multiples of 4. And then we have x is equivalent to 1, so we square both sides. And we see that x squared is also equal to 1. So all the integers a equivalent to 1 mod 4 are in the equivalence class 1. So that's just all the numbers in the form 1 plus 4n for some integer n. So that's -7, -3, and so on. And we can do these for the next few. And we see that the 4 here is equivalent to 0, and the 9 here is equivalent to 1. So all of the integers in the form 2 plus 4n is in equivalence class 0, and all of the integers in the form 3 plus 4n for some n as an integer is in the equivalence class of 1. So we know that 0 is the union of these two sets, which is basically just all of the even numbers, and 1 is the union of these two sets, which is all of the odd numbers. And we know that 0 contains all the even numbers, 1 contains all the odd numbers. So the union of 0 and 1 is z, and since z is our original set right here, it means that 0 and 1 are the only equivalence classes that are possible, and we found them right here. So, now, suppose that A is this set of numbers, and consider the relation divides on a set A defined by A pipe B, if and only if A divides B. So, the first thing is proving that it's a partial order, and the way we do that, we think back. We have the properties of reflexivity, anti-symmetry, and transitivity, and those are the things that we need to prove. So, to prove that it's reflexive, we just define x to be in a number in the set A. We know that x divides x if it's not 0, and since 0 is not in the set A, we know that all x divides x where x is just some number in A, and that proves that it's a reflexive relation. Okay, now we can prove anti-symmetry. So we take this if statement and we suppose that x and y are numbers in set A such that x divides y and y divides x. So the property that x divides y means that x has to be less than or equal to y, and the property that y divides x means that y is less than or equal to x, which gives us this equation. And you've probably seen this before. You just apply sandwich theorem. So it just shows that x is equal to y, where x and y are some numbers in A. And since we've proven this then statement, we can say that it's anti-symmetrical. So let's prove transitivity. We define three numbers right here in set A, x, y, and z, and we have the properties that x divides y and y divides z. So by definition, we can just make it so that y is equal to ax and z is equal to by for some integers ab, and then we can just sub this y into this second equation, which gives us z is equal to abx. Since ab is an integer, we know that x divides z, so this relation is transitive. So we know that it's reflexive, anti-symmetrical, and transitive, and therefore it's a partial order. So now let's draw up a Hasse diagram. And a Hasse diagram is basically just a way to represent a partially ordered set. So a partially ordered set is just a set where a partial order is applied onto. And the way you do it is generally you would just go up in values. So you would start at the lowest element, which is 2 in this case. Since we're just doing numbers, we can just go by magnitude. So we have our relation as A divides B. So generally on the bottom, you put the numbers that don't have anything relating to it. So in this case, the numbers that don't have anything dividing it. And in this case, it's the primes, since the only other numbers that divide the primes are 1, but 1's not in the set, right? So our lowest tier would be 2, 5, 3, and 5. And then we go to our next number, which is 6. So since it uses elements of the first level, you write 6 up here, and then these lines basically say that it relates. Then we have 15. 15 is divisible by 3 and 5. And we have 30. So 30 is divided by 6 and 15. The reason 30 is on the third level is because it uses the elements of the second level. And now let's go to 35. 35 is actually on the second level because the only element it has that relates to it is 5, and 5 is in the first level. Now we can move on to 70, which we know relates to 70 and also relates to 2. Then we have 105, which relates to 35 and 3. And then, last but not least, we have 210, which relates to 30, 70, and 105. So the reason we don't have to draw lines like this is because it's transitive, right? So if 2 relates to 6, and 6 relates to 30, and 30 relates to 210, we can safely say that 2 relates to 210. So this line right here is not necessary. Right. So now let's find these elements. So we just need to define what a maximal element is, and a maximal element is an element such that no other element relates. So it doesn't relate to. So okay, sorry, I misread. The minimal elements are elements such that no element relates to the minimal element other than itself. So in this case, the minimal elements are primes because the only number that divides it is 1, and 1's not in set A. So we know that all of the composite elements have something that relate to them, which we can see in the Hasse diagram here, since every other element except 2, 3, and 5 have lines before them. And yeah, that just explains what I said, since 1's not in there and 1's the only number that divides it other than itself. 2, 3, and 5 are the minimal elements. And the least element is an element such that every element must be related by that element. So let's say that A is the least element. It would mean that A would have to relate to both 2 and 3. And since 2 and 3 are just elements of A, so we know that 2 and 3 are co-primes, so A must be 1. But since A isn't, like 1 isn't in A, there can't be a least element because there's no element that satisfies the condition that it relates to every other element. So there are no least elements. And then maximal elements, it's elements such that there are no elements that are maximal elements that relate to... Sorry, I'm kind of dyslexic. Yeah, so maximal elements, it just means there aren't elements that it relates to. So if you see in our hash diagram right here, we have 2, 5, 3, all of it relates to another element. 6, 15, 35, they also all relate to another element. And 30, 70, 105, they all relate to another element. And the only element that doesn't relate to others is 210, so that's our only maximal element, which is right here. And the greatest element is an element such that every element relates to the greatest element. So we know that every number in A divides 210, which is from the hash diagram, since all of the lines just go to it. So we can safely say that 210 is our greatest element. So find two elements of A that do not have a greatest lower bound and explain why that is. So given two elements, the lower bound are all of the elements that relate to both of them, and the greatest lower bound is the greatest element of these lower bounds. And greatest in this case would be magnitude, because we're dealing with numbers. So consider the greatest lower bound of 2 and 3, we kind of did this before. An element that relates to both would divide both 2 and 3. 2 and 3 are co-prime, and the only number's 1, but 1's not an A. So there's no element which relates to both 2 and 3. And since there are no lower bounds, there can't be a greatest lower bound. Okay, so this is our fourth topic, which we're doing right now, enumeration probability. Do you have any questions on the previous topic that you want answered? No? Or would? All right, let's move on. So, let xi and y for I is equal to 1, 2, 3, 4, 5 be 5 distinct points on the Cartesian plane with integer coordinates. Prove that at least one midpoint of two such points has an integer coordinate. The reason why I labeled these words red is that this is an indicator that you need to use pigeonhole principle. So you have to prove something is at least some n, where n is just an integer. So this is a picture that I took from the Easter show where they have some pigeons cooped up, and they have 4 pigeons here and 4 pigeonholes. So we see that each pigeon occupies the pigeonhole. So if we were to say introduce a 5th pigeon, right? You know, right here. This is my coolest pigeon, yeah? It can't have any space other than a space that's already occupied by a pigeon. So there must be at least one pigeonhole such that there are at least 2 pigeons. So this is just pigeonhole principle. Given that there are n plus pigeons sorted across n pigeonholes, there must be at least one pigeonhole with 2 or more pigeons. Then there's also generalized pigeonhole principle, which is just you have n pigeons and k pigeonholes, and then there's at least one pigeonhole with n on k ceiling or more pigeons. So we know that the midpoint of 2 points, A, B, and C, let's say, would be defined by this. And to have the average of two integers be an integer, they must either be both odd or both even. And that would mean that AC and BD must have the same parity. And in this case, if you don't know, parity just means odd or even. So, coordinates are represented by two numbers, x and y. And all of the combinations of parity for x and y are given by odd, even, odd, even, odd, even. So we see that there are 4 cases, right? But we have 5 distinct points and only 4 cases of parity. In this case, our pigeons are the points and the pigeonholes are the possible cases of parity, which means that there must be at least 2 points which share the same parity for both coordinates. And from our last thing, we see that that would mean that those 2 points would make a midpoint with integer coordinates, so there must be at least one midpoint such that 2 points have integer coordinates. Okay, so next question. How many different ways are there to distribute 80 identical balls and 40 distinct lollipops amongst 8 children? So the first part is with no further restriction. We can actually see that these are 2 sub-problems, right? So the first one is distributing 80 balls amongst 8 children, which are identical. And then the second one being distributing 40 distinct lollipops amongst 8 children. And then the answer to A is just multiplying alpha and beta, since multiplication principle, since we have these 2 cases right here. And then we need to find all of the combinations which are available. So, you know, we can first look at the first subproblem, which is distributing the 80 identical balls amongst 8 distinct children. Generally, if you see children, it's probably going to be distinct. You know, you can't have the same identical child. So we can have the amount of balls for each child be represented by x to the I. So we can make an equation something like this, which you might see, it's called a summation equation, which is just x1, x2 plus x3 all the way to x8 for the 8 children equal to the 80 balls that we have. So in this case, xi is a non-negative integer because a child can receive 0 balls. And for this equation, we have a general solution for n identical objects and r distinct boxes, which is given by this formula. We just plug our numbers in where r is equal to 8 and n is equal to 80, and then that gives us our final amount of solutions, which is 87C7. And the formula only works when they are non-negative integers, so it can be 0. Okay, now distributing the 80 distinct lollipops amongst the 8 children. The general solution for distinct objects and distinct boxes is taking the number of boxes and then putting it to the power of the number of objects right here. So in this case, it's 8 children and 40 lollipops, so it's 8 to the 40. And the reason is because every single object has r choices to go to. So in this case, every lollipop has a choice of 8 children to go to. So that's 40 choices of 8, 8 to the 40. Okay, so now we know that alpha is 87C7 and beta is 8 to the 40. We can just multiply these together by multiplication principle, which gets us 87C7 times 8 to the 40 ways to distribute the objects amongst 8 children. Okay, so now we have B, which is with each child getting at least 1 ball and exactly 5 lollipops, and these are just additional restrictions. And we can see obviously which one it applies to. So the first one, it looks at the balls, and the second one looks at the lollipops. So we just add this line, which is the fact that each child must get at least 1, and then this line, which says that at least each child gets exactly 5 lollipops, and this applies to alpha and beta each. So again, the answer to B is just alpha times beta from multiplication principle. So again, we can represent it in this summation equation, except this time they're all positive integers. And if it's n identical objects and r distinct boxes, we have this formula, which only works if they are positive, so they can't be 0. And in this case, r is equal to 8 and n is equal to 80, so we have 79C7. Then in this, it's a little different. We have each child choose 5 lollipops from the pile of 40. So the first child would have 40C5 ways to choose the lollipops, and afterwards, that means there would be 5 less lollipops for each subsequent child. So the second person would have 40 minus 5 to choose from. So that's 35 ways to choose. And we can just multiply these. So we find that it will be 40C5, 35C5, all the way to 5C5. And let's just simplify this a little. And we know that this is the ways you can distribute 40 lollipops so that each child gets 5. We know that NCR has this form called the factorial form, and we can just transform it to the factorial form. We know that every denominator and numerator share some term like this. So we can actually just cancel all of these, and we're left with 40 factorial on 5 factorial to the power of 8. And this is our most simple form right here. So we have alpha, which is 79C7, and we have beta, which is 40 factorial on 5 factorial to the power of 8, and we just multiply them by, and that's all of the different ways to distribute the 80 objects amongst 8 children. So now we have a summation equation, but some a bit different restrictions, which is xi being odd and xi being less than 7. So when we have a summation equation like this and restrictions, the first thing we look at is the thing that makes it so that the xi can't be consecutive integers. So the thing that's restricting it from being 0, 1, 2, 3, 4, and etc., which is in this case being odd, because making it odd makes it so that it can only be 1, 3, 5, etc. So to fix this, we can rewrite x to the I is equal to 2yi plus 1, where yi is an integer, and this is just the form of an odd number, as you may know. So we know that x to the I is greater than or equal to 1, since it can't be 0, as it's odd, right? So we can sub this in, and then solve for yi to get yi is greater than or equal to 0, which is our first thing. And then we can also sub it into the second restriction, which we can solve to get yi is less than or equal to 3. And essentially what we've done is we do the substitution to all of the x to the numbers, and then we can collect the terms and stuff, and then just make these y terms the subject right here. So minus 6 from both sides, and then divide by 2, which gets us 15. And what we've done is we turn this question into this secondary question with a lot less conditions, where the only one is just yi is less than or equal to 3 for non-negative yi's. And if we have a thing where it restricts all yi to be less than a single number, we can look at a total, So we can instead look at the total number of cases and then minus the complement. The complement is just the thing such that you can take, it considers every single other case that the first condition didn't. So in our case, the complement to having yi less than or equal to 3 is having every single yi greater than 3, or in this case, greater than or equal to 4, since they're integers, right? And we know that the total of this equation without any restrictions can be given by 20C5 from our original formula. So let's find the solutions for the complement where yi is greater than or equal to 4, and we need to find out when there is one such yi, two such yi, and three such yi. There can't be 3 or more because there are only 15 objects. So if there are 4 or more yi's which are greater than or equal to 4, that means there would have to be 16 or greater objects, and obviously there are 15, contradiction, you know. So we have the case where it's one such I, so we can consider the case where y1 is greater than or equal to 4. We can let it so that y1 is equal to a1 plus 4, which makes a1 greater than or equal to 0, and then we can just let the others stay the same since the others just are greater than or equal to 0. We sub these in, make it so that the a terms are the subject, and then we have this equation where the only condition is ai is greater than or equal to 0, so the total amount of solutions is 16C5. We can do this for 2, so we let y1 is equal to a1 plus 4, and y2 is equal to a2 plus 4, and then the others are just yi is equal to ai. We can solve for the ai terms, then it gives us this equation. We sub it into the formula that we had before, which gives us 12C5 solutions, and then we could do it for 3 terms, which just follows the previous things, and then gives us a total of 8C5 solutions. Now, we use something called inclusion-exclusion principle, which is essentially just a formula which allows us to find the amount of objects within a bunch of sets unions. So, in this case, we have AI, which is represented by when yi is greater than or equal to 4. So, a1 would be when y1 is greater than or equal to 4, and so on. And a1 intersection a2 is when both y1 and y2 are greater than or equal to 4. So we know that the amount of objects in a1 and a2 are equal, because if we go back to this y1 case, we can actually just replace these with y2 and follow the process, and it would give us the same amount of solutions right here. And we could do it with every other y. So we know that in this case, all of these a1, a2, and so on, they're all equivalent to a1. And we can do the same thing for ai intersection aj and ai intersection aj intersection ak for ijk that are some integers. So we have the inclusion-exclusion principle just applied here. So we have these 3 terms which you have to simplify. We already know that these 2 are the same as these are the same, and these are the same terms. So we just need to find out how many terms there are. So for each thing, you just look at how many ways you can choose, in this case 1, so 6C1. How many ways you can choose 2 elements, so 6C2, and how many ways you can choose 3 elements, which is 6C3 right here. And then you just simplify by subbing in the stuff that we found already. And now we have our total right here and our complement right here. So it's total minus complement. And then we know that there are 86 solutions. So let S be the set of all 14-letter words where it comes from the English alphabet of 26 letters and there's no repetition. So the first part just wants us to find how many words there are altogether, and that's 26 letters where repetition isn't allowed. We choose 14 and order them, so it's just 26b14, simple as that. So a way to find inclusion or exclusion principle is if we need to know how many of something there is, and also the or, which is just equivalent to union. So these words hint at inclusion-exclusion, so we just need the inclusion-exclusion to be applied like this, where A Julia are the words that contain Julia, A Tony are the words that contain Tony. Oh, sorry, I don't think I actually explained the question. So the question wants all of how many words there are in the set S which contain Julia or Tony inside it. And then right here, this term is just all of the words that contain both Julia and Tony inside the word. So we just need to find the amount of words where Julia is inside it individually and Tony is individually, and then all of the words with Julia and Tony both as subwords. So the way we can do Julia is we can consider that there are 14 spaces, and we want all the words such as Julia are inside it. So we can choose the letters for Julia. We can see that 5 are chosen here, which gives us 9 more spaces. And since there's no repetition, there are 21 more letters in the alphabet. That's just 21C9 ways to choose the letters. We also want to preserve the order of Julia, which is what the brackets mean. And we can do this by treating this as an entire letter. We have 9 more letters, so that's 10 objects in total, so 10 factorial arrangements. And then we can just see that there are 21C9 times 10 factorial arrangements we can do. And then for Tony, it's a similar process. Tony's been chosen, so there's 10 spaces left, 22 letters left, so 22C10 ways to choose the letters. We have to preserve Tony, so that gives us 11 objects since there are 10 more letters, so 11 factorial arrangements, and therefore 22C10 times 11 factorial words with Tony. So now we just need all the words with both Julia and Tony inside it, so we can have both of them chosen already, which gives us 5 more spaces and 17 letters in the alphabet, so 17C5 ways to choose these letters. And we want to preserve these words, but they don't have to be together, so we can treat both of these words individually as letters. So Julia is its own letter and Tony is its own letter. That gives us 7 objects, 7 factorial, so that's 17C5 times 7 factorial. Now, we just apply inclusion-exclusion principle, and we sub these in, which gives us this expression for how many such words there are. Fred. So, how many words are there in S such that all 5 vowels are contained? And we can just choose the 5 vowels like we did before, which gives us 9 more spaces and 21 more letters since there's no repetition. So that's 21C9. And we just need to arrange the 14 letters, which is 14 factorial. The vowels don't actually need to be in an order, so we can just do 14 factorial. And that gives us 21C9 times 14 factorial. And that gives us to the next question. So we have 4 friends, June, Alex, Wayne, and Joe. They're playing bridge, and a standard pack of 52 playing cards is dealt, where every player is given 13 cards. So the first subproblem is find the probability that June and Wayne are dealt all 13 spades. So probability is just number of cases with the requirement where the requirements to be dealt all 13 spades and the total cases. So there are 2 players, so 26 cards dealt, and there are also 52 cards in the deck, so it's just 52C26 as our total amount of cases. Then we want all the 13 spades to be dealt, so that means 13 of the 26 slots are taken by the spades, which gives us 13 more cards and 39 remaining cards. So if cards are being dealt from a deck, then we just assume that it's not, there's no repetition. So that gives us 39C13 ways to choose the remaining cards. And then it's just using this probability formula. So we have 39C13 over 52C26 as our probability. Now, we need to find the probability that the cards dealt to June and Wayne contain at least one complete suit. So this at least once, and probability should hit inclusion-exclusion, because if we look at our thing, we need to find the number of cases with the requirement, which is just how many cases there are, right, with the requirement. And since the requirement is having at least, which is also equivalent to just the union of having one of each, I'll just explain it later. So we know that the total is 52C26 from the last question, and this is just inclusion-exclusion principle. We know that a way to get a single complete suit, it has 39C13 ways, and there's only one way to get dealt 13 spades and 13 hearts, since there are 26 cards being dealt within 2 suits and 26 cards between the 2 people. So there's only one way for 2 suits, and we can't have 3 or more suits, which is because it would require 39 or more cards. And of course, we have 26 cards, contradiction. So we apply inclusion-exclusion principle, which is just the union of having all of the spades dealt to you, all of the hearts dealt to you, all of the clubs dealt to you, and all of the diamonds dealt to you. And we know that it can only go up to 2, so there are max 4 choose 2 cases. So we, from the previous thing, we just see how many terms there are, which is 4C1 and 4C2. We simplify, we sub in the numbers that we've already found, and we just simplify again. That gives us a probability of 4 times 39C13 minus 4C2 over 52C26. So, given a straight path of width n to be laid using 1x2 blocks, so this is an example of a path of 8, 1, 2, 3, 4, 5, 6, 7, 8, being laid by these 1x2 blocks. Let an be the number of ways we can lay a path of 2 by n. So in this case, this would be 2 by 8. We need to find a1, a2, and a3. So that's the paths which have a size of 2 by 1, 2 by 2, and 2 by 3. So let's draw this up. So the simplest case is a1, which has a space of 1 and 2. And clearly there's only one way to use 1x2 blocks, which is just like vertically here. So a1's equal to 1. And then we have a2, which has a 2x2 case. So there are 2 ways we can do this, which is 2 vertical blocks and then 2 horizontal blocks. And that would give us a2 is equal to 2. And then we have a3, which we can actually just form by expanding on the previous things. So we know that we can add a vertical block to the A2 case for each A2 case, which would give us 2 cases. And then we can actually also have 2 horizontal blocks added to the A1 case, which would give us 3 cases in total. So that would be our A1, A2, and A3. Now, we want to obtain the recurrence relation of AN and explain the answer. So this is our recurrence relation, and the reason this is because let's just divide it up to each individual term. So from our previous thing, we've shown that if we have n as 3, all of the n minus 1 cases can be built onto an n case by adding this 1x2 block in a vertical fashion, which gives us this a n minus 1 term. So, which is why it's 1 times a n minus 1 in the recurrence relation. And then we also have this a to the n minus 2 case, because for every path that we can have with a n minus 2, we can also build up to a length of n by adding this 2 horizontal pieces. So that case obviously isn't covered by the first a n minus 1, because the a n minus 1 only considers having the vertical blocks, which is why we have this a n minus 2 term and giving us the relation an is equal to an minus 1 plus an minus 2. Now, we have this we need to find the general solution to this recurrence relation. This is probably going to be an information dump, since you need quite a bit of theory to solve these. So the first thing is, this is how a recurrence relation is defined, where it's just a bunch of an terms, and it's equal to some function of n, fn, and ci, which are the coefficients. They can also all be functions of n. In this case, we only deal with linears. So the linear property is when all of the coefficients are constants, and we also have the homogeneous property, which is when fn is equal to 0, then the non-homogeneous property, which is when it's not equal to 0 and it's some function of n, or like a constant as well. So to solve for a linear homogeneous order 1, It's usually given in the form an is equal to r an minus 1 for some random r, and that just has a general solution of an is equal to a times r to the n for some constant a. So now we can look at linear homogeneous order 2, which is given by this general form, an plus p times n minus 1 plus q n minus 2 is equal to 0, which is what gives it the homogeneous property. And we can equate the coefficients we have to something called a characteristic polynomial and then solve it to give us alpha and beta, and these just determine what type of solution that we have. So if alpha and beta are both real and non-equal, then a general solution is given by this form where it's alpha to the n times a plus beta to the n times b. If they are equal and real, then it's given by a times alpha to the n plus bn times beta to the n. And if they're complex conjugates, which are in the form r with the exponential of plus minus I to the 0, the general solution is r to the n times a cos n theta plus b times sine n theta. And in this case, a and b are just some random constants. So now for non-homogeneous solutions, for a non-homogeneous equation, a solution is given in the form an plus is equal to hn plus pn, where hn is the solution if it were a homogeneous recurrence, and pn is the particular solution. So pn has to be guessed, and it can be guessed by mirroring fn. So if fn is a constant, you would make pn a constant. If fn is a polynomial, you would make pn a polynomial of the same degree. And if it was an exponential, it would be a constant times an exponential of the same base. And if it's a product of the previous two cases, then you would correspond it with the product of the corresponding guesses. And a guess doesn't work if hn and pn share a term, which we'll see later. And if that's the case, we have to apply our previous pn by n to form a new guess. Okay, so now let's get to our actual thing, which we know is a non-homogeneous linear second order recurrence. So it means it would have this form. So if it were homogeneous, we would just have this term become a 0, which is what we have here. We can put it into the characteristic polynomial right here and solve it to show that the solutions are the same, which are 3. And so therefore the general solution is given by a times 3 to the n plus bn times 3 to the n. So now we can look at the particular solution where fn is 5n times 3 to the n. And we want to mirror this, so it's a linear times an exponential with base 3. So a possible would be pn is equal to this linear. So what you would do is if it were, even though it's like a 5n, you would have the linear be a cn plus d because you want it to be any possible linear, and it's the same for quadratic. So if it was like an n squared, you would make the guess like a n squared plus bn plus c. So you times it by the 3n, so it's a linear times exponential, and c and d in this case are just some random real numbers. So it only works if they don't share any terms, and we know that this term cn times 3 to the n is actually equal to this term bn times 3 to the n, so this doesn't work. We can multiply it by n to find this new pn, but if you see there's this term which is also equivalent to this term, so it doesn't work out, and therefore we just need this pn where we times it by another n and it gives us this pn. To find the constants, we sub in pn in place of an, so we have this equation right here, and we just simplify it out to get this equation, and then we can equate coefficients to get two simultaneous equations, which we solve to get the constant c and d, and Therefore, the particular solution is n squared and then the constants subbed into the linear right here times 3 to the n. Now we have the hn from previous work and the pn from the previous work. Then we just combine it together, which we have our an. And that is the end of our presentation. Thank you all for coming, genuinely. There's a secondary one which will cover logic and proofs and then graphs on Thursday, 2 to 4. And these presentations are also uploaded onto our website, so you can check them out during your StuVac. All right, stay safe and see you next time. Also, like, if you have any questions, like, I can stay back and ask